Now, we're going to look at the case when two particles collide. And what we have is M1 has an initial velocity of V1, and M2, in this case here, maybe it is moving with a smaller velocity of V2. Now, we are putting the velocity in the same direction. And it's possible to do that by changing the frame of reference. And according to Newton physical law, it doesn't change if you change the position of your reference frame. So what we have here is that the relative motion in this direction, let's say this is the x direction, and let's reduce all velocity in the y and the z direction to 0. And that at some point it will collide. Now let's say after the collision, the velocity would be u1 and the velocity will be u2. The mass obviously doesn't change. Now, as we said before, you can consider a frame of reference whereby you have v equal to m of m1 of v1 plus m2 v2 divided by m1 plus m2. And therefore, if you use that frame of reference, then considering v is equal to 0, then you have the motion of these two particles very similar to here. Basically, it would be, all of these would be at rest, whereby if you move one, you have the other particle bouncing off. But we're talking about two masses here. So if we talk about, let's just keep it up here like this. If we have a particle of two of these speed hitting the other one, what you see is that very obviously the one of the bead would hit the other one, and then it would just simply stop, and the other bead would move off with the equal velocity. If we take out two more beads and just look at these two bits here, what you see here is even more clear, that you have one bead hitting the other bead, imparting the velocity entirely to the other bead and remain stationary. When the bead comes back, it will just stop again, and then it will just do this sort of motion, right? So now this is an example of an elastic collision. Elastic collision. What it means is that the collision has total transfer of energy from one bead to the other bead. So if before collision is a velocity v, the velocity upon hitting the other bead would be v also, moving the other way, where this first bead is totally stopped. So this is completely elastic because no energy is lost in the collision. Now, you may hear the slight sound, tick, 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 tick sound, which is a loss of energy, of kinetic energy into acoustic energy. But let's just assume that's relatively small compared to that of the kinetic energy. All right? So what we have here, the question is, after the collision, the velocity changed to u1 and u2. The question is, how do we calculate u1 and u2? Now, if in case you have totally elastic collision, meaning that the energy is not lost other than a complete transfer of kinetic energy from one particle into another one, in this case here, or there's a redistribution of the kinetic energy among the two particles that collided. So the question is, how do you calculate V1 and V2? Now, there's something called the coefficient of elasticity given by the formula C of R. And that has the formula which is, in this case here, if after the collision you have the velocity u1 minus u2 divided by v2, let's just do u2 first. u2 minus u1 divided by v1 minus v2. Okay? So this measure of velocity, in the earlier case, what you have is that v1 minus, the initial velocity v1 minus v2, if this is the positive direction, is positive. And then u2 will be the resulting unit velocity moving up this way. So u2 minus u1 would be in the same direction. So in this example, v1 minus v2 is equal to u2 minus u1, because u1 is now 0. So in this example, what you have is that this equation is equal to 1 for the bouncing beat example. All right, so we call that situation completely elastic collision, or elastic collision for short, whereby all energy is transferred to the other. Now, on the other hand, if it's completely inelastic collision, which means that the two spheres would totally combine together, the two objects would totally combine together to form one. And the resulting velocity is no longer u1 or u2, but basically you have the resulting velocity u1 is equal to u2 is then equal to, in this case here, v given by this formula here, this particular formula here. All right? So this would be completely elastic, whereby you would have a loss of kinetic energy, because it's just like two objects bang into each other, they no longer bounces back out. Now, if it's completely elastic and two equal objects that collide together would totally reverse course at the same velocity going either way. But if it's totally inelastic, and if these two objects are coming to each other at the same velocity, and they will come to a dead still, all that kinetic energy in this case here is converted into heat because of a collision. It's just like two wet objects, and when they combine, it seems that all kinetic energy is lost, but actually the energy is converted into heat, and therefore the particle would stop altogether. So here, what we have shown here is basically that you can use the conservation of energy, and also with a coefficient of elasticity to derive completely the resulting energy or the resulting velocity of the particle.